A drop in utility frequency such as the one described to 59.8 or 59.75 Hz, followed by a return to normal, can stem from several potential causes. Firstly, a grid disturbance can be a factor. A sudden change in load, such as a major industrial facility turning on or off significant equipment, can cause a temporary drop in frequency across the power grid. Secondly, a synchronization issue could be the reason. If multiple power plants are connected to the grid, their frequencies must be precisely synchronized. A temporary synchronization issue between these power plants can cause a deviation in frequency that propagates through the grid. Thirdly, equipment malfunction is a possibility. A malfunctioning generator or other essential grid equipment can introduce frequency fluctuations into the power system. These fluctuations might be localized or spread depending on the severity and location of the malfunction. Fourthly, load shedding can induce frequency drops. If the power grid is overloaded and approaching instability, the power company might implement load shedding, intentionally disconnecting non-essential loads to prevent a widespread blackout. This sudden reduction in demand can cause a temporary, although intentional, drop in frequency. Fifthly, transmission line issues can also lead to frequency problems. A fault or outage on a transmission line disrupts the normal flow of power, causing imbalances and potentially leading to a drop in frequency. Sixthly, weather events such as severe storms, lightning strikes, or other extreme weather conditions can disrupt transmission lines and cause frequency fluctuations. These disruptions can range from minor sags to complete outages affecting the grid's stability. There are reasons why the power company might not have been immediately aware of the frequency drop. The drop in frequency might have been localized to a specific geographic area, or it might have occurred during a time when the power company was not closely monitoring a particular section of the grid. It's also possible that the power company was not operating any equipment at the time that could have caused the issue, leading them to believe that the problem originated elsewhere. Furthermore, they might not have received reports from other customers experiencing similar problems, especially if the issue was highly localized or transient. The impact on a UPS or uninterruptible power supply system is relevant here. UPS alarms are typically triggered by frequency deviations that fall outside of a predefined acceptable range. A drop in frequency below the alarm threshold can cause the UPS to switch to battery backup mode, ensuring that the critical load it supports continues to receive uninterrupted power. If a frequency drop like this occurs again, there are steps that should be taken. Firstly, check the incoming metering again to confirm the readings and rule out any measurement errors. Secondly, contact the power company again and provide them with the specific time and measurements of the frequency fluctuations. This detailed information will help them investigate the issue more effectively. Thirdly, consider using a UPS with a wider frequency tolerance to prevent future issues of this nature. A UPS with a broader tolerance range will be less likely to switch to battery backup mode during minor frequency fluctuations, improving the overall reliability of the system. It's important to understand how power grids maintain stable frequency and voltage. Power grids operate by balancing the supply of electricity with the demand. When demand exceeds supply, the frequency drops, and conversely, when supply exceeds demand, the frequency rises. Power plants adjust their output to maintain a stable frequency, typically 60 Hz in North America. Voltage regulation is maintained through a combination of reactive power compensation, transformer tap changes, and generator voltage control. These systems work together to ensure that voltage remains within acceptable limits throughout the grid. Common power quality issues besides frequency deviations include voltage sags, voltage swells, harmonics, and transients. Voltage sags are short-term reductions in voltage, while voltage swells are short-term increases in voltage. Harmonics are distortions of the sinusoidal waveform caused by nonlinear loads, and transients are sudden, short-duration bursts of energy. All of these power quality issues can negatively impact sensitive electronic equipment and can be mitigated through various power conditioning devices. Frequency is a critical parameter in AC power systems. It directly relates to the speed of rotating electrical machines such as generators and motors. Deviations in frequency can cause these machines to operate inefficiently or even become damaged. Sensitive electronic equipment, like computers and data center servers, rely on a stable frequency for proper operation. Large frequency excursions can lead to data corruption, system crashes, and hardware failures. Power companies use sophisticated control systems to maintain grid frequency within tight tolerances. These systems rely on real-time monitoring of grid conditions, advanced control algorithms, and high-speed communication networks. Despite these efforts, unforeseen events can still cause frequency deviations. Understanding the potential causes of these deviations and their impact is crucial for maintaining the reliability of electrical systems. The National Electrical Code, or NEC, doesn't specifically address frequency deviations directly, but it does provide guidelines for ensuring the safe and reliable installation of electrical equipment. Articles 100 through 900 cover topics such as wiring methods, overcurrent protection, grounding, and equipment installation. These articles are all relevant to maintaining power quality and preventing equipment damage from power quality issues, including frequency deviations. Power monitoring equipment plays a crucial role in detecting and diagnosing frequency deviations. Advanced power monitors can record frequency, voltage, current, and other electrical parameters over time, providing valuable data for analyzing power quality issues. This data can be used to identify the source of frequency deviations and implement corrective measures. When specifying a UPS system, it's important to consider the frequency tolerance of the UPS. The frequency tolerance specifies the range of frequencies over which the UPS can operate without switching to battery backup. A UPS with a wider frequency tolerance will be more resilient to grid disturbances and less likely to switch to battery backup unnecessarily. Regular maintenance of electrical equipment is essential for preventing frequency deviations and other power quality issues. This includes inspecting and testing generators, transformers, switchgear, and other critical equipment. Proper maintenance can help identify potential problems before they lead to equipment failures and grid disturbances. When experiencing frequency deviations, it's important to document the events carefully. Record the time, date, duration, and magnitude of the frequency fluctuations. This information will be helpful when communicating with the power company and troubleshooting the problem. Understanding the different types of loads on the electrical system can also help in diagnosing frequency deviations. Large inductive loads, such as motors and transformers, can cause voltage sags and frequency fluctuations when they are switched on or off. Nonlinear loads, such as electronic devices with switching power supplies, can generate harmonics that distort the sinusoidal waveform and affect frequency stability. Power factor correction can improve the efficiency and stability of electrical systems. Power factor correction involves adding capacitors to the system to offset the effects of inductive loads. This reduces the amount of reactive power flowing through the system, which can improve voltage regulation and frequency stability. Harmonic filters can be used to mitigate the effects of harmonics generated by nonlinear loads. These filters are designed to block specific harmonic frequencies, preventing them from propagating through the system and causing problems. Surge protection devices, or SPDs, can protect sensitive electronic equipment from voltage transients caused by lightning strikes or other events. SPD diverts surge current away from the equipment, preventing damage. Isolation transformers can be used to isolate sensitive equipment from the electrical grid, reducing the impact of power quality issues. Isolation transformers provide a separate power source for the equipment, preventing noise and disturbances from the grid from affecting its operation. Uninterruptible power supplies come in different topologies, each with its own advantages and disadvantages. Common UPS topologies include online, offline, and line interactive. Online UPS systems provide the highest level of protection, as they continuously power the load from the battery. Offline UPS systems only switch to battery power when the utility power fails. Line interactive UPS systems provide some voltage regulation and surge protection, but they do not continuously power the load from the battery. The choice of UPS topology depends on the criticality of the load and the level of protection required. When selecting a UPS, it's important to consider the load requirements. The UPS must be sized to handle the total power consumption of the connected equipment. It's also important to consider the inrush current of the equipment, which is the surge of current that occurs when the equipment is first turned on. The UPS must be able to handle the inrush current without overloading. The battery capacity of the UPS determines how long the UPS can provide power during a utility power outage. The battery capacity should be chosen based on the amount of time required to safely shut down the connected equipment or to allow for an orderly transfer to a backup generator. UPS systems require regular battery maintenance to ensure that they are ready to provide power when needed. Batteries should be inspected regularly for signs of corrosion or damage. The batteries should also be tested periodically to verify their capacity. Some UPS systems have self-testing features that can automatically test the batteries and provide an alert if they need to be replaced. Backup generators can provide a reliable source of power during extended utility power outages. Generators can be powered by diesel, natural gas, or propane. The choice of fuel depends on the availability of fuel and the cost of operation. Generators should be sized to handle the total power consumption of the connected equipment. It's also important to consider the starting current of the equipment, which is the surge of current that occurs when the equipment is first turned on. The generator must be able to handle the starting current without overloading. Automatic transfer switches, or ASs, are used to automatically switch between the utility power and the generator power. The ATS monitors the utility power and automatically switches to the generator power if the utility power fails. When the utility power is restored, the ATS automatically switches back to the utility power. ATS ensure that power is restored quickly and seamlessly during a power outage. Power quality audits can help identify power quality problems and develop solutions. A power quality audit involves measuring various electrical parameters, such as voltage, current, frequency, and harmonics, over a period of time. The data is then analyzed to identify any power quality problems. Based on the results of the audit, recommendations can be made to improve power quality and prevent equipment damage. Power quality monitoring systems can provide continuous monitoring of power quality parameters. These systems can alert users to any power quality problems, allowing them to take corrective action before equipment is damaged. Power quality monitoring systems can also be used to track power quality trends over time, which can help identify potential problems before they occur. Consulting with a qualified electrical engineer or power quality expert can be helpful in diagnosing and resolving power quality problems. An electrical engineer or power quality expert can assess the electrical system, identify potential problems, and recommend solutions. They can also help with the design and installation of power quality improvement equipment. Firstly, remember that frequency is measured in hertz, which represents the number of cycles per second of the alternating current. Secondly, understand that a stable frequency is essential for the proper operation of electrical equipment. Thirdly, remember that frequency deviations can be caused by a variety of factors, including grid disturbances, equipment malfunctions, and weather events. Fourthly, realize that the power company may not always be aware of frequency deviations, especially if they are localized or transient. Fifthly, realize that UPS systems are sensitive to frequency deviations and may switch to battery backup if the frequency falls outside of a certain range. Sixthly, confirm your readings with your incoming metering equipment, specifically checking the time, date, duration, and magnitude of the fluctuations. Seventhly, provide the power company with specific information about the frequency deviations. Eighthly, consider using a UPS with a wider frequency tolerance. Ninthly, implement regular maintenance procedures for electrical equipment. And tenthly, consult with a qualified electrical engineer or power quality expert if you are experiencing persistent power quality problems. Remember that large inductive loads, such as motors and transformers, can cause voltage sags and frequency fluctuations when they are switched on or off. Also, nonlinear loads, such as electronic devices with switching power supplies, can generate harmonics that distort the sinusoidal waveform and affect frequency stability. Power factor correction can improve the efficiency and stability of electrical systems, and harmonic filters can be used to mitigate the effects of harmonics generated by nonlinear loads. Surge protection devices can protect sensitive electronic equipment from voltage transients caused by lightning strikes or other events. And isolation transformers can be used to isolate sensitive equipment from the electrical grid, reducing the impact of power quality issues. Uninterruptible power supplies come in different topologies, including online, offline, and line interactive. The choice of UPS topology depends on the criticality of the load and the level of protection required. When selecting a UPS, it's important to consider the load requirements, including the total power consumption and the inrush current of the connected equipment. The battery capacity of the UPS determines how long the UPS can provide power during a utility power outage. UPS systems require regular battery maintenance to ensure that they are ready to provide power when needed. Backup generators can provide a reliable source of power during extended utility power outages. Automatic transfer switches are used to automatically switch between the utility power and the generator power. Power quality audits can help identify power quality problems and develop solutions. And power quality monitoring systems can provide continuous monitoring of power quality parameters. Lastly, it's always a good idea to consult with a qualified electrical engineer or power quality expert if you are experiencing persistent power quality problems. Remember that the stability of the electrical grid is a complex issue that requires careful monitoring and control. By understanding the potential causes of frequency deviations and implementing appropriate mitigation measures, you can help ensure the reliable operation of your electrical equipment. By following these recommendations, you can better understand and address utility frequency drops and ensure the reliable operation of your critical equipment.